Alrighty then. It says we're live, so we must be live because it's red, obvious. Hey guys, what's going on? Memes here. And today we're going to be discussing the Planck length. What the heck is a Planck length? Where the heck does it come from? Where do we go? Something Cotton Eye Joe. I don't know. But now, yes, I see you there, Poindexter. Welcome, thank you for joining. So let's not belabor the point. So let's jump right into it. What the heck is a Planck length? So we're gonna start with a little picture, a little thumbnail, if you would here. All right, and we can zoom in. Okay. So basically this is just a thumbnail. So I went right to Wikipedia and I just took a screenshot. And then I put in the Planck time over it because this is how it is defined. All right. So for those of us that may not be aware how certain notation works, because notation has never confused anybody except for me. The reason why I say this is if you don't happen to be aware of certain things, then you might confuse things. For instance, this notation is lowercase t. That's important. Sub p. And within this is a capital P. Why? Because it's standing for Planck. That's the name. It's basically the subset of Planck units. The small t means time. That's how I now remember it, because when I was going through some of Thad's calculations before, there were two TPs. One was a capital T. That's Planck temperature. It's about 10 to the 32 Kelvin. The Planck time is about 10 to the minus 44 seconds. Wrong dimension, and 76 orders of magnitude difference. I'm just saying it was a little frustrating for me personally when you're making mistakes. Okay. Now again, what is it? It's defined by the square root, which is interesting, of h bar, the elementary unit of action, aka Planck's reduced constant. So it's Planck's constant divided by 2 pi. So rather than having to write 2 pi for every like cycle or everything, yes, it's expressed like that. I also learned something new the other day that apparently joule seconds, it's joules per hertz, which is the most obvious thing in the world, aka hertz, a cycle. Okay. And we got big G here, the Newtonian gravitational constant, whatever the heck that is. And then we're dividing this up here by the speed of light, the maximum of speed in the medium of to the fifth power. Okay. Why the heck is all this stuff here? Long story short is if you throw all these into a calculator, this has dimensions of like mass, length squared, and then divided by time. Big G has like length cubed because it's talking about a volume thing, divided by mass, and then acceleration, which is time squared. So, basically, those things will cancel out, and you will get a unit, a single dimension of a thing, and it will be time. It happens to be like 5.391 times 10 to the minus 44 seconds. Okay. 1 second is approximately 1 Mississippi. Okay. This would be about, take that 1 Mississippi and divide it by, okay, how high do we need to go? Okay. Trillion is 9 zeros. Trillion is 18 zeros. Trillion is 27 zeros. Trillion is 36 zeros. We need almost 5 trillions. So it's like, what is it like? 100, no. 10 billion, trillion. There you go. Yeah. Dividing that 1 Mississippi. Wicked small, as we say up here in the greater Boston area. Okay. So rather than just showing the dang thumbnail, and let's actually get to a point, shall we? Okay. Yes. Welcome. Yes. Uh-oh. Nerdy? I mean, I tend to agree with that statement. I don't know. I don't know. Different. The Wolfram Physics Project may suggest maybe there's something below that, about 10 to the minus 100 seconds, according to my calculations. Or Wolfram Alpha's got around the same magnitude. Hey, welcome, Bill. Good to see you, my friend. Yes, we're just discussing. Basically, we're just going to make this Planck week rather than. I'm like, all right, I need to put out some consistent content. What's something I can talk about for at least 5 days a week? I'm like, well, I got about five core Planck units that I would argue. And again, I'm very biased because this was introduced to me by Thad uh, with his generalized formulation. As far as I can see, you can do it this way. And again, I don't think there's one particular way to try to figure out and model the world. I think different folks have different strengths. Like the Wolfram Physics Project is Professor Wolfram thinks very computationally. He's like, all right, I think in a set of basic rules, that's cool. You can go in whatever direction you want. Um, might there be some that are a little bit more useful, in my opinion, than others? Sure. This is just how I think about it. Okay. So what the heck is a plank? Go to our friends at Wikipedia, and I apologize, I didn't put the link below, but basically, if you just put in, I just Googled Planck Time and the first Wikipedia page that came up. And again, take this for what it's worth. So the generalized thought here is we've got something here. This is basically the Planck scale. So we're thinking there's a unification at one. Oh, one, you say? Uh, but the claim is because if you got a Planck energy here, okay, so that would be the energy equivalent of a Planck mass. So this is approximately, for human observers like us, about the energy in a lightning strike. Lightning strikes may vary. Okay. So basically, that would be made up of a Planck time. Excuse me. You would have a Planck mass, and you would have to have length and time squared. So you'd have to c squared, this Planck length, divided by Planck time. You square them both. There might be a little asterisk there, according to Thad's model, but I'm going to say at least 7 decimal places those things are going to match. Yes, the speed of light is Planck length divided by Planck time. Okay. Um, so basically what they're showing here is in terms of time, and now this is the claim. They're now doing density and everything. So basically, if you would have a black hole, in one Planck mass black hole, it's basically going to have like a radius of like 2 Planck lengths because there's a factor of two in there, because I guess that's how it is. Um, So if you're going to follow the Schwarzschild radius, the interesting thing is as the black hole or whatever the heck that dense or at least starting extremely dense object is, because if you caveat, there seems to be a coincidental thing that if you take approximately the mass of the observable universe and you divide it by the volume of the observable, long story short, if you took the mass of the observable universe and you crammed it into a black hole, the black hole would be about the size of the observable universe. Is that actually the case? I don't know. I'm not an outside. I can't say. I can't say. It's one of those things where if you happen to be within the system, sometimes it can, can complicate things. Uh, but long story short, this is the general size curve, or basically linear relationship there. And then you're talking about a Compton limit. So basically, as you were to go up or down in mass, you're going to hit like the Compton wavelength first thing. So that seems to be a boundary of things of a particular size. And again, I'm not a particle physicist. So we have a notion of oneness there. Take that as you would. And again, I don't have a PhD in physics. I don't even have a degree in physics. But I did graduate from the Wolfram Summer School program. So take that for what it's worth. I finally finished my LinkedIn. I forgot my old passwords. I'm there like, where the heck did I work? When did I work there? I'm like going through copying off my old archaic profile. So disorganized. Okay. And do a reading from Wikipedia because at least I went through at least the beginning of this, and I view this page many times. So again, Planck units in particle physics and physical cosmology. Planck units are a system of units of measurement defined exclusively in terms of four universal physical constants. C, the speed of light. Big G, the Newtonian gravitational constant. H bar, the elementary unit of action. And KB, Boltzmann's constant. Expressing one of these physical constants in terms of Planck units yield a numerical value of 1. One is useful. They are a system of natural units, defined using fundamental properties of nature, or specifically properties of free space, rather than properties of a chosen polytope object. I did need to mouse over these things and see what the heck they were. I'm like, polytope object, isn't that something poly a a prototype object? Sorry, prototype object. Okay, I apologize. Yeah, polytope's on my mind. Basically, four-dimensional Pythagorean solids, I believe. All right. Sample or a model. So basically, the kilogram, as many people were aware, and I think even like yeah, when I was growing up, it's like, what is a kilogram? It's the mass of a platinum iridium cylinder that's stored somewhere in Paris. It's like that seems kind of crazy, but apparently we found it better than using a cubic deciliter of water around. I think was it the triple point? It was either triple point around freezing, or is that maybe the same thing? Um, but oh god, so much random knowledge of things in my head. Okay. The long story short is it's based upon constants of nature. That was basically the whole gist of the project I did at the summer school is yes, that was also the way I actually technically discovered that. And actually, Thad had been saying this for a while. It's like as we better come to know and define the constants of nature, because he even said, like, yeah, it is. We're refining our definition of the second and stuff like that. So it's like, all right, it's a second is the SI or the International System Unit of Time. Again, it's about 1 Mississippi. So basically, the long story short is you can divide that 1 Mississippi into a lot of little bits, let's say. I'm not sure if that pun is supposed to be intended, but who knows? We'll see if computation rules the day. All right. Originally proposed in 1899 by German physicist Max Planck, they are relevant in research on unified theories such as quantum gravity. The term Planck scale refers to quantities of space, time, energy, and other units that are similar in magnitude to corresponding Planck units. This region may be characterized by particle energies of around 10 to the 19 GeV or 10 to the 9 joules, units of energy. Uh, Time intervals of around 5 times 10 to the minus 44 seconds and lengths of around 10 to the minus 35 meters. Okay. So, so basically, these are equivalent ones within the system. Now, I may have a little bit of an issue when they say a similar in magnitude to corresponding Planck units. It depends upon the dimensionality. Because again, it's like you have the speed of light, it's like, yeah, about 3 times 10 to the 8 meters per second. All right, 10 to the 8. But Planck time and length are 10 to the minus 35 and minus 44. Why? Got two really small things, and the magnitude difference between them is speed, because speed is the length, it's the distance you go, so you get a length. And how long did it take you? You go 100 kilometers per hour, it's like, all right, you've traversed 100 kilometers. What was the period of time? 1 hour. Boom. There you go. You're doing science. We just happen to refine those into, we like using seconds and meters and stuff. I'm sorry. Listen, you can be an imperialist if you want to. Uh, it- I'm just saying it's a, when somebody brought that up at a political town hall about it's like, when are you going to get us out of the dark ages and bring us into the SI or metric system or something? That political candidate had never been asked that question before. Thought it was an interesting question, and I gave it minimal thought until more recently. Rampant opinion there. Okay. All right. Let's see. Let's see. Bill is County Planck energy is Elando or XNP Planck area matches. Oh, okay. Um, Not everybody might know what that is. It's Elando are basically something thermodynamics and stuff. I think there's a logarithmic property there. So you can use your thumb. Well, here's the thing. Even in the units project that I was doing, nerdy, when you're saying it's a reference thing. And here's the thing: the cubit was literally, it's like, all right, it's like the length of your like forearm to the tip of your finger. It's like you just got to build a farm. Yeah, your arm may change slightly, but if it's good enough to build a home and survive and live on that scale, it seems to work pretty well. It's just when trying to get magnitudes and magnitudes, it's kind of like you're trying to engineer a precision engine or something like that. It's the precision you're probably going to want. I don't even know the scale. Bill would know. I think he was in the industry. Uh, you want like micron precision. So all I know is when I would pick up car and driver or any of those other things, it's like you could you would just see that there would be these zeros to this precision and everything. And apparently, if we're trying to figure out reality, we want to have as much precision as possible. All right. All right. Inverse femto. Let's go. Oh. Let me see. Think. Okay, yeah, yeah. So it's like 4 pi surface area there, and that's why. Oh, that's why it's 4 pi squared. So that's why it's 16 pi for a minimal black hole because it's got the two m in there. Uh oh, that makes sense. I learned that in high school and finally have a reason to know it and remember it. Thank you. Uh, all right, cool. Where are we at? Where are we at? Let's see. All right. So basically, the numbers that they just listed there are approximately the energy equivalent of the Planck mass, the Planck time, and the Planck length, respectively. At the Planck scale, the predictions of the Standard Model and the quantum field theory and general relativity are not expected to apply, and quantum effects of gravity are expected to dominate. One example is recommended by the conditions in the first 10 to the minus 43 seconds of our universe after the Big Bang, approximately 13.8 billion years ago. Okay. I only noticed that sometimes you'll hear 13.7, 13.8, 13.78. It's interesting just because, oh, look, 137 potentially is the first couple of numbers there. But yeah, there's deviation over there. But then again, it's like, hey, I wasn't there. I I personally, and again, I'm very biased on this. I think the age of the universe, again, I think it's greater than 14 billion. Is that a stunning and brave prediction? Not really. Uh, what am I arguing over? Like 200 million years, something like that. It's like other people propose other things. I just think if we have more time, that'll explains a lot of other things. Again, there could be a whole lot of other effects, but I'm just like, if we have more time and it was some form of a steady-ish state, then again, I'm a blasphemer. Don't listen to me. So the four universal constants that by definition have a numeric value of one when expressed in these units are C, the speed of light in a vacuum, aka the medium, whatever that might be. G, the gravitational constant. H bar, the reduced Planck constant. K sub B, the Boltzmann constant. Variants of the basic idea of Planckians exist, such as alternative choices of normalization that give other numeric values to one or more of the four constants above. The whole idea is as long as it's coherent, aka F equals ma, force equals mass times acceleration, energy equals force times the distance, and power is energy divided by time. At least according to the Wikipedia diagram that Thad showed me, and then when you go through it on the project, and at least the project, it's amazing what you can do with simply just multiplying or dividing units effectively of one, just using time and length. That's what I did for one of those things. It's like, well, I knew that. I knew if I multiply a force times a distance is going to get energy because force is mass times acceleration. Acceleration is just a distance traveled or a length divided by time squared. So it's a length traveled by a distance per length per unit of time per time. You're just dividing it twice. So AKA it's going to get faster and faster. You're going to accelerate. If you multiply that by another length, you just have two lengths up there. Two lengths divided by two times. Wait a second. If you're dealing with a Planck unit, minimum of length squared divided by a minimum of time squared. Oh, speed is just length divided by time. Square that, you just got your c squared. Bada boom, bada bing. You got your energy there. I probably should be using the board, but maybe we'll in a little bit. So to not belabor the point again, just as a general exercise, going through these actually did help me. So it's like again, I ain't anybody's boss or teacher or anything like that. But it's like, okay, so you got your little force thingy here. So you got your force, your Newtonian gravitational constant, mass one times mass two, divided by the distance or the radius between them squared. Okay. So basically, force, you can rewrite this. So basically, you rewrite this, you can put this outside, but it would just be in the numerator anyway. So the Planck force times the Planck length squared, and then they're put it in. Oh, they're putting in the Planck mass there to derive out something else, or should that? Oh, yeah, yeah, yeah. They're swapping. Okay, okay. Big G. So they're okay. So they're multiplying. Oh, oh. Can that be cubed then? Mass one, mass two. Oh. Okay, so it's force. I should probably actually do that out. Okay. I did it out before. It confused me. It's okay. I have homework. Screenshot my homework to do that again because I don't instantly. Uh, so force divided by Planck force, aka if you get a mass there, you're dividing by the Planck mass, the radius. You're expressing it in one. The force divided in by the reference or the effective Planck unit of one. See, I did a whole project on this and I still get confused talking about it. So I've also spent a good fair bit of time on Wolfram Alpha. Why did I want that to be? I just like the. Okay, I'm sorry. I like making it bigger so I can see and then everyone else can see. Okay, so as I've now thoroughly embarrassed myself, let's get to the actual point of the video. So these are the modern values, so we can express values of length, mass, time, and temperature here. Okay. Um, you can argue that temperature is an energy, and that's basically how we convert back and forth, and we need Boltzmann's constant in there. Uh, long story short is if you also want to incorporate electric charge, you're going to have some form of the Coulomb's constant. Basically, you need the electric constant in there somewhere. Why? Because electricity appears to be a thing. If, if we didn't have something like that, then we wouldn't be able to do it. So there's different ways to express it. You could either express the Planck charge. In this value, it gets you 10 to the minus 18, or you could express it like this. So what's the difference here? Well, uh, the difference is it's either about 3.3 the elementary charge, so the charge of an electron or proton, and then the Planck charge would be equivalent of 3.3 or the square root of the Planck structure constant here. I happen to be more amenable to that because if you square this, you will get like 137.03599 if you actually put it in there. Um, again, this is basically apparently 1 over 137 is a lot sexier, so to speak, than 1 over 11.7. This was kind of how Professor Feynman liked thinking about it. Um, Again, it could be personal opinion there. Long story short, you need the electric constant in there. That's the one thing you need. So if you want to express temperature, you need Boltzmann's constant. You need the electric constant, and other than that, you can pretty much form everything with a Planck length, Planck mass, and Planck time. Because at that point, you got mass, you can get c squared, bada boom, you got energy, and then you can convert energy via different transformations and equations between electricity and or electric stuff. Charge related stuff would be the proper term. Because SI doesn't use Planck charge, it basically just uses current. The ampere, which again, I'm not saying that that's one way to do it. There may be more optimal ways. I would argue, but okay. So the Planck time, as far as we know, is a minimal unit of time. And again, I have a little argument here. I would say it should be small t, but and you could use big T right there rather than like one of the characters from Fall Guys or something like that. It's I know it's probably the symbol for degrees Celsius or something like that. Someone's going to be like, "You would." I've never successfully completed an entire physics class. Believe me, unless you consider the Wolfram program of physics class, more like a series of different lectures and interesting discussions. Okay. So it is defined by Planck time, and again, this is I'm just saying it's using small t there. Then again, whatever. It's defined by this thingy here, which we showed there, and so basically the square root of h bar big G all divided by c raised to the fifth power. Why is it raised to the fifth power? I don't know. Outside rampant speculation, and you could potentially parameterize 5 dimensions to reproduce all the stuff and things we need. Basically, these 4 units and then some form of a Planck charge. Again, that wasn't me. Thad just noticed that and he pointed it out, and seems to be true. Okay, this Planck time, as far as magnitudes go, at least of these units, um, including the Planck charge, has the greatest magnitude. It's about 5.391247 with an error of 16 last two times 10 to the minus 44 seconds. So you could divide one Mississippi into that many little pieces. Uh, or you would just divide it. Yeah, yeah. And Nerdy was saying it might be a potential refresh rate. I'm of that mind because also, and again, I'm not a professionally trained physicist, so take this statement as it would. It's a little bit of a mimetic here. At least I was talking with that at one point, and so it's like within quantum field theory. To my knowledge, they teach you about well, what is a electron? It's an oscillation. It's a vibration in the electron field. The Higgs is a vibration in the Higgs field and everything. So we got all these vibrations in these 17 elementary fields doing all the different stuff and things to make up our world. It's like, all right. And then they never talk about it again. I don't know if that's true. I'm not a particle physicist. I haven't taken QFT. Uh, but it's like, all right, it's an oscillationist field. All right, cool. Uh, maybe there's all those fields, and that's like, wait. It's like a frequency vibration. Well, if you just do 1 over the Planck time, you get Planck frequency just because it's 1 over Planck time. Just gives you the reciprocal of seconds, which is hertz, the Planck frequency. It's that ginormous number right here, 10 to the 43 hertz. I'm like, and again, I'm not the first person to point this out. People have been saying this for a while. Again, that John gentleman that was on Fractal Woman's channel. At one point, he's like, yeah, it's what if we just had the Planck frequency because we think the Planck's time's a thing, and we just invert that, we got a maximum of frequency. Can't can't all those other fields just live within the field of the Planck? I don't know if that makes any sense. Um, because I'm just saying, if you added all the other stuff in the field up, I don't think you're going to exceed the Planck frequency per whatever unit basis you want. Um, just an opinion there. Okay, so it's redonkulously small. Okay, so let's actually see what other folks. Da, 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 da. All right, it's a couple of billion years between friends. Yes, Matt. Yes, Matt. Okay, let's break this back. I've just been going on Wikipedia. This is just generally accepted stuff, or at least most people. Many folks within the scientific community, of the things that people argue over, I don't think this is one of the main ones. Now, again, people argue over the basis, the best ways to express this. I remember I watched, oh God, Neiman or something, whoever the Demystify Sci folks had on again. I guess allegedly got a bad rap because it got a lot of audience capture initially and was kind of in some more esoteric areas and maybe making some overzealous claims. But then again, it's like, I mean, heck, I hang out with plenty of interesting folks. Um, so I should be fair as long as he is willing to admit, yeah, I kind of got captured by my audience. I kind of like leaned into something. But he was saying it's like a lot of physicists, the general convention when you're going to talk about units and stuff like this. And again, I heard Professor Carroll say this. It's like all good physicists set h bar equal to one because the generalized idea is if you have these base units and they're expressed in one, which you can do that. So if h bar equals big G equals C equals one. Now, those are in different dimensions, but the claim is it's like, all right, you got H bar, it's the one of action. You got big G, it's the one of gravitational acceleration. You've got C, which is the one of speed. And seeing as these units are made of like H bar, G, and C, these yield one. But what the gentleman on Demystify Size most recent episode, what he was saying is you probably shouldn't do calculations like without the units because it could be telling you something. Now again, like that adds additional things, and basically, long story short, is you have to keep track of your units. That's a really big thing. That's that's something that like that seems to be pretty good at doing, and even Kurt Mungle, he has his quick short little, I think it's like a half hour video or so on dimensional analysis and back of the envelope calculations, kind of going through some of this stuff. So, taking me a while. Am I good at it? No. Can I trudge through the basic algebra? Yeah, just because I I got taught that I can just rewrite these things as this. Because depending on how you want to express it, if there's all these different okay. How about this? Let's uh let's do Planck and let's see. Okay, again, this is another Planck unit. But okay, Planck intensity, what L sub P, that's supposed to be the Planck length. That's actually capital I. Again, it's the only reason I knew this is just because Wolfram Alpha told me after a calculation. Okay. So it gives you this stuff. It's like, all right, interpretation, energy flux density. All right. Heat flux, irradiance, a thermal dose rate, electromagnetic energy flux, metabolomic rate, radiant flux density, surface power density, area heating capacity, energy flux of electromagnetic radiation, radiative forcing, sound intensity, electromagnetic radiation dose, rate. Frequency integrated spectrum irradiance with respect to frequency. Radiant existence, self-radiant existence. Oh my God. Okay, so they only listed like, I don't know, maybe like 12 or 15 different dimensions. At one point, I think it was last year when I had come across this, there was literally like 60 different interpretations. Why? You click on this. Because when you look at least the dimensional building blocks, metabolic rate as a physical quantity, you could say watts divided by meters squared, which the Planck intensity is expressed in. It's ultimately, you boil it down, it's a mass divided by time cubed. The negative sign means it's just in the denominator. So if you express this as mass, it'd be mass, and then divided by time. So since it's positive, it's to the first derivative. Basically, it's the thing itself. That's what it is there. You go back again. We go down to the bottom. Oh, look, Planck intensity is a mass divided by time cubed. Okay, so long story short is all those interpretations have the same dimensional framework. Um, those are a whole bunch of varying words that essentially are measuring the same basic unit dimensions. The magnitudes they're expressed in might be a little bit different depending on what field you're working in and what you're doing there. Uh, but I wonder if I click this, it'll give me more. Or they realize maybe listing 60 to 80 different interpretations was okay. Okay, so I think they cut it down. Um, yeah, because I think it is my one of my favorite units now is crab, a unit. Yes. Yes, a crab is also a unit of mass divided by time cubed. I just remember when I got that number, I was going through, it was like, what is this? Like something, something crabs? I'm like, what? What? Because I'm thinking, crabs, I don't walk a bit sideways and stuff. No, it's okay. The physical quantity is the frequency integrated graded spectral irradiance with respect to frequency. Oh, wait, no, it's just okay. But rather than saying all that, they just called it the crab. So one basic unit of the crab is, well, what is that? That's 1 microwatt per kilometer squared. That's an interesting unit. That's equal to 42 crabs. Listen. I understand. That's a fascinating thing with units. You go through all these things, and you're like, wait a second. It seems like reality, or at least I would claim some scientists have some sense of humor. Reference the tortoise coordinate from black holes. Wait, turtles all the way down, Lonnie? I digress. Where were we again? I think I need to get to the point here. Let's see, what do we got here? Oh, that's where we left off. I apologize, Matt. Okay, let's again. We've covered stuff that seems to be a thing. We've proved at least showed that apparently at some point people were measuring. Okay, what is this even actually? They were measuring energy flux density in units of crabs. Yeah, make this stuff up. That's why I'm like, sometimes real life is better than fiction. Oh, maybe a wee bit AD&D. ADD. Yes, AD&D. Advanced Dungeons and Dragons, my friends. Uh, this is the point where I'm supposed to play that clip, aren't I? All right. So if we're conjecturing ahead, take it away, Professor
Although
Wolfman.
this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles. various people are commenting on the outrage of hacking the universe on a MacBook Air. Um,
So the absolutely crazy thing is, no, I agree with you. It's no, but even when I did that summer school project, one of the things it's like, what is a meter? It's obviously the distance between the North Pole and the equator by root of Paris divided by 10 million, because duh. Like the second is an earthly convenience. Why? It's like, we like one Mississippi, so it's like I can put about I don't know, about 60 Mississippis in a minute, and then I don't know, 60 minutes in an hour, and we'll do that by like 24, and you get pretty close. We got like some remainder or something like that there, but it's an earthly convenience. Um, I mean, what are the chances that we end up developing and refining a basics that really had some legitimate connection that ultimately it's the transformations that are supposed to matter? So, perhaps, no, I'm not a mathematician. Something tensor transformations, because the tensor is supposed to represent some form of a map between one thing and another. So I'm just thinking, well, it's like if you take the maximum speed, you divide it by the minimum time, you should get the minimum length. That's just the whole concept. So it's like you just got stuff in a things, and they might be bigger or smaller. So that's why if you're looking at different ratios, if you find a ratio, especially if it seems to hold, or as Max Planck did, you could help chunk and solve different problems. That's pretty cool. What type of sorts of things would be maximally resistant to destructive interference patterns? Hmm. Uh, I saw the beginning of an interesting video where apparently the Google or Microsoft, I don't know, there's like a big company, and they had it might have been a recording studio where they had like this room, and it had all these kind of like that insulation, and it was supposed to be all this different material. Long story short, it's supposed to have like negative like sound capacity. Like if you go in there, it's so eerie to a human like us, where we're used to being in. It's like, oh, there's different sounds and stuff like that. It's like people apparently start getting freaked out after a little while, because you're there, and it's like you literally like hear your heartbeat and everything else, just because the acoustics are like so like minimal in there. Um, I have no idea if that's a thing. That would be maximally destructive interference patterns. What is a destructive interference patterns? Are we just talking about an oscillation enough to hold on? Destructive interference. Destructive interference occurs when the maximum of two waves are 180. Ah, okay. So instead of like wave cancellation, where it's like, wait, no, it's if that they're at the same frequency, they cancel out. Okay, so if they're aligned to cancel out, a positive displacement of one wave is canceled exactly by the negative displacement of the other. Or is it they have to be inverse? Hold on. Swinburne. It might be saying that interference is a situation occurs when the crest and trough two waves meet. Okay. So you get a oh, okay. So they net out. Okay, so if you're adding them together, so if you got two waves, they would amplify. Okay, so it's just you got one going the other way, you got the anti. Uh I mean they would cancel out. I mean, oh, is that why there's a two in the two GM divided by C squared for a Schwarzschild black hole? Because if you technically had two Planck energy photons and they were to go at each other, wait, no, they would cancel out. No, hold on. Net energy needs to cancel. But no, because that would be a two Planck mass black hole. I don't know. That's a good question. Oh no, because no, a photon is a translation of energy, typically. Um, See, this is the weird thing. It's like you hear it's like stuff must be conserved. But then it's like, well, in a limit, it's like, well, maybe not locally. I think globally, things kind of need to be conserved. I would think. Isn't that one of the whole? It's like, all right, universe is expanding. Why? Well, because dark energy is a constant. Since dark energy is a constant, we don't know what it is. We call it dark energy. Often we express it in the cosmological constant, or some may infer it's the cosmological constant, which is expressed in inverse meters squared. And you're like, Nani? That's a crazy thing. And I think that if you're going to say dark energy is a constant thing, but if things are expanding, it's like, all right, so if the overall size of the universe is getting greater, but it's remaining a constant, where's that energy coming from? Now, if one believes that perhaps our universe, so to speak, or our realm, was inside a black hole, hey, that's an easy one right there. It's like, hey, stuff goes into a black hole's going to get bigger, it's going to do its stuff, do its things. Okay, I can kind of grok that. Kind of makes sense now. The amount exchange in order for that to happen, even though according to our equations, the density of I don't know. Uh, my thing is, it's like, all right, but if we had a amount of stuff, if you're getting bigger, your natural thought is, well, then it would go down. Some measurements now, especially the CMB seems to be right at what, about 67 and a half, 68 kilometers per megaparsec per second, or something. Those crazy units of like the spreading this out of stuff, so to speak, is happening. It's like, okay, I can try to think about that now. Where does that lead us? Does that lead us anywhere useful? I'm realizing we're supposed to be talking about the Planck time here. Oh, hey, it led us to that. Uh, da, da, da. Oh, Bill. No. Yeah, Bill was a meteorologist. He worked in measurement patterns, most crisp in all frequencies. Yep. Okay. Yeah. Yeah. Ah. See, that's the interesting. Okay, to my knowledge, aren't at least within the realm of quantum computing, whatever that may or may not be, aren't like the most powerful ones analog quantum computers because like we need to do that because that's kind of the point because we're trying to use complex numbers which are real plus like some rotational okay, that crazy little block sphere thing with the axis and then the flag that points around that you'll see in some of those videos. It's uh, let's see. Oh yeah, no, well, see, that's the great part about the internet. Like you never know who you run into. And there's a lot of folks around. Uh, let's see. Oh, the anechoic chamber. Ah, cool. Yeah, no, I remember that chamber was pretty crazy. But all right, so the Planck time. So as far as we know, basically, according to the best of our measurements and stuff right now, we believe that we run into these units. So basically, we have a minimum of time. A lot of times, just even just having conversations, it's like if you say something about that, it's like people hear words and stuff like that. Like see like a PBS space time video, they're like, "Oh yeah, you talk about like the Planck length or something like that," and you're like, "Oh, the Planck length, Planck time." You're like, then you see like 10 to the minus 35, 10 to the minus 44. It's like, all right. So, on a basis of one thing, ridiculously small. So people are like, oh, it's the Planck scale, it's just small stuff. Okay. The problem you run into with that is, again, we're also talking about different dimensions. And again, a lot of times when people talk about, oh, different dimensions, it's our base thought is If you say different dimensions in comic books or movies, very often you're talking about some alternative reality, another universal realm, so to speak. If you're talking about just our dimensions where we live, it's like, all right, it's let's one dimension. Point. Okay. No, excuse me. No, I mean three. What's zero dimensions? Zero dimensions is a point. It's like an infinitesimal whatever thing. One dimension. What's one dimension? It's like a line here. What's two dimensions? It's this box here. Typically a screen that you may or may not be watching on. Um, Now, the other, and to be actually, the interesting thing is if you're listening, you're also incorporating another dimension because there's some frequency being oscillated around. So you could say you're also listening with time, which I don't know if that's actually accurate, but sounds good, right? Uh, okay. The Planck mass, though, is also quite small, about the mass of a mote of dust. A mote of dust that, if it fully released its energy, is like a bolt of lightning. Is that how wizards work? I think wizards within Dungeons and Dragons are supposed to have reagents that they use because they need verbal, they need to be able to speak typically. They need somatic components, they need to use their hands. Again, unless you have the particular skill that allow you to do other things. And then they require some form of a reagent to do things. Is that how we get that spell? Fireball? They're just like, all right, words, some signs, some reagent, fireball. I see. I kind of want to create like a universe, a game, or something like that, where it's like, what if rather than having to have like a particle accelerator stuff like that, it's like you could just do something like that, kind of like the Tony Stark thing, where it's like you have those things, but I'm biased, so I'd probably have like a Wolfram Alpha GUI or something. It's like, take this. Oh, this rock is like 1.2 kilograms. What can I do with like 1.2 kilograms? Okay, you're on the calculation, C squared. I need to get this baddie off me. Oh crap, 10 to the 17 joules. Okay, you then realize that's overkill if you're going to do an energy blast. Because it's like, unless it's a sufficiently powerful opponent, yeah, yeah, you're hurtling that 1.2 kilograms and doing the C squared transformation. You're releasing of magnitude the energy released by the Krakatoa explosion. For those of us that may not be aware of history within the past 100 or so years, Krakatoa was an island that existed. After the eruption, it didn't exist anymore. People lived there. I don't think anybody survived, unfortunately. See, that's the fascinating thing. You look at it, it's like, wait a second. Why? Why? Well, Planck mass gives you about the energy of a lightning strike. That's 10 to the minus 8. That's in reference to 1 kilogram. So 1.2 kilograms, since you have a negative 8 power, Planck energy is 10 to the 9 joules. So you're just going to go up 8 more powers of joules. That's just the unit of energy. We just call it the joule because we named it after, was it Prescott Joule? Something like that. James Prescott Joule. That's Joule. James Prescott Joule. Okay, so I kind of remember. The intuitive representation. Yes, we're using things of 1 meter, blah, blah, blah. Okay, so the joule is literally defined as the SI units, your unit of mass, a kilogram, times the meter squared, and then times inverse seconds. AKA, we're dividing by seconds. That's kilograms times meters squared divided by seconds. AKA mass and then speed squared. And if it happens to be the maximum of speed, you're going to get your maximum energy. Right? Yeah. All right. And again, this is the only reason I'm really being able to grok this is, or at least some of this, so to speak, is literally that telling me, okay, so basically you can construct like the measurements or at least the parameters of quantum field theory using five things. Maybe we need to cancel all the infinities. That may very well be the case. And again, even Professor Feynman at one point is like, Feynman diagrams have to be like the dumbest way to try to compute these things, but I haven't found a better way. And again, I'm probably mischaracterizing that, but if you're the whole, we're going to assume it's going to take all these paths. Well, what are the most likely paths? Probably the path it's going to take. It's kind of sounds very Occam's razor-ish, one might think. Um, okay, so we have the Planck time here. So we did our conjectures. Oh, hello, Rick. Welcome, my friend. We were just bantering a bit about this, that, and the other thing. Talking a little bit about uh, decoherence. Oh, do dimensions have volume? So here's the thing. We take three dimensions of space, aka length. That's how we get space as observers like us typically interpret it. Now, might there be some greater thing down there? Maybe. Maybe it's turtles all the way down. Who knows? Um, but basically, oh, this is what I had meant to talk about earlier. Uh, very often, observers like us, when you say dimensions, you're just thinking the dimension of space because we'll say, oh, well, we live in our three plus one dimensions, and very often we don't consider what that might be or something. It's like, oh, three spatial dimensions, one time. Time is just seems to be a thing that happens. And then, oh, we live in like some 3D world, yada, yada, yada. Okay. The problem is, again, your comic or MCU adaptation might be dimension, obviously different reality or whatever, different realm. Cool. Your dimension to a normal thing is like, oh, okay, one dimension you got a line, two dimensions like a sheet of paper or something like that. Three dimensions is us, we think. Stuff around us. Okay. Now, again, this might be a language thing, and other languages might have it better. But dimension, again, if you're going to go within a method of parameterizing stuff doing things, that's kind of the best definition I have. Uh, because and again, I think it's a testament to humanity that we've been able to like parameterize the best things in the best way we have. The sheer fact that things seem to work very well, and again, we're not done. We're not done as far as I know out there. There doesn't seem to be any publicly known way to unify all the different stuff and things within physics. Okay. I'm not saying it doesn't exist. It might. It might, but I cannot say. Um, but okay, so Planck time. What the it's this thing here. All right, so we got Planck time. So what happens if I don't know, let's multiply it by C. I might have to write out speed of light. Planck time times C. Oh look, you get what? Planck length. Because it's literally defined. Well, it's defined by the other thing, but this is well, you get a maximum speed, and then you multiply it by time because the as a unit is length divided by time. Okay. So if we multiply it by that, we put another Planck time up there, so we just get our unit of length. Kind of like we just did it the other way. It's like, all right, let's break C apart. Oh God, that's a terrifying thing to say. Oh, I did that totally wrong. Supposed to divide it. Oopsie. Oh, this actually gives us Planck acceleration. which is an interesting thing because so I don't expect anybody. Okay, some folks here probably know about this, but all right. If you see this thing right here, the UNRWA temperature or the Hawking temperature, okay. Some folks may have heard of that whole Hawking radiation. What is that? Basically, this is the claim that if you hit a certain acceleration, you're going to be emitting like heat. We haven't observed this as a theoretical thing. Many people believe it's a thing. I know it's a thing. No. But the interesting thing is that if you see these, this should be a little baffling here because this is a little bit below the Planck temperature. The Planck temperature is at magnitude 10 to the 32 Kelvin. This is only at 10 to the 31 Kelvin. What's the difference? Okay, so the difference, oh, let me refresh this. So the difference between this, okay, let me express it like this. So we got that many Kelvin. So just divide it into the Planck temperature. Planck temperature, divide by the thing. That's not useful. Wolfram Alpha does not like the Planck temperature. Here, we'll do this. Ugh. It doesn't like that, but I just click on the thing. It gives me it within the unit system. Oh, God. Don't mind my killing my own video. Okay. Oh, back. Back. Uh, what am I doing? Copy. There we go. All right. So when we just put the units there, Planck temperature divided by that. 2.83. Wait a second. I see what's going on here. What excuse me. Let's inquire. What might 6.283 or something be? Oh, look, it's 2 pi. The interesting thing is, yeah, we have the Planck time, but very often, kind of like with Planck's constant h, that's a thing, but we very often express it divided by 2 pi, which is h bar. So basically, in order for the Planck acceleration to be a thing, you still need to multiply it by 2 pi, which is an interesting thing because also if we go back to the divide by time, does happen when I divide by. Okay, that's not what I meant to do. Basically, if you just do Planck length, I'm sorry. This is what, again, nobody's ever been confused about units. Oh, look, we get a frequency, the maximum frequency. Then we divide Planck length by c. Lucky, hey, we get the Planck time. Yay! Okay. So this is generally the concept of like, all right, these things are going to relate to each other. But as we just saw, though, those were some units, but the equivalent Planck temperature is up by 2 pi. So may consider that a rotation. So if we go back to the Planck time, okay, you might see this. You're like, that's interesting. Now, what happens if we played? We play, we do 1 over Planck time. All right, we get the Planck frequency. Now note, when we go down here, this is an interesting thing. The photon energy of a photon is because basically, if you're doing the Planck frequency, it's oscillation. So basically, if that's the maximum frequency we can have, given the energy of a photon from that. Okay. So if we look at this, we're gonna show what it is. Okay. Okay, I know this is interesting. I know this is interesting. Don't get excited. Yes, it's showing 137 micrograms. It's not actually 137 micrograms. It's like 136.65 or something like that. Yeah, I saw that. I started losing my mind at one point, and then I went down, and it's rounding up to 103 cents. These are the places where it's like, especially if you're going down a Wolfram hole, you'd be like, "Oh my God, this is great!" Like it's like, "Oh, this must be what it is." And then you go down past three decimal places, and you're like, or you get more than three significant digits, and it's like, okay, because if you see 6.28, you're like, "Oh, it obviously must be pi." Good chance it might be pi, but it also might deviate greatly. So it's like, again, if we only have limited data, like if you're going to estimate, I can say like claim that the neutron, its effective RMS charge radius or whatever that might be, square mean charge radius is going to be about 8.40 uh, times 10 to the minus 16. I want to say femtometers, but it's like a tenth of 0.840 femtometers, I believe. Um, I can say that because I still think we have like zero significant digits. I think we have the correct magnitude, but it's actually zero significant digits for the actual neutron's radius. Uh, it's thought to be eight for the first digit. Okay. So, yeah, stunning and brave to propose two digits that we have no idea. Now, I could say that because limited data. If you're going to try to explain the anomalous magnetic moment of the electron, you gotta get a match like 14 significant digits. It's somebody that tried to do it. I didn't do it. That I think found an answer. Probably still kind of hand wavy, but it's like, well, that seems to be the limit of our knowledge utilizing quantum field theory and stuff. Fantastic. Just saying time is fundamental. Well, yeah, it, it kind of seems like the bottom turtle to me, but then again, I am biased here. Oh, at least this last thing. Okay. So if we notice here, this is actually greater than the Planck energy. I just think that that should be noted because number one, it okay. Well, this and the Planck energy are they both greater than 1.8 gigawatts? I think so. I think that may be why they did it. Okay. So long story short is if we take that again, basically we did one over Planck time. We got the Planck frequency. You'd have a Planck frequency, blah blah blah. Let's divide by Planck energy. Oh God, the lag is real. Wow. Oh, this is terrible. Wow. Wow. I'll even close my other little music thing. Oh, there we go. Okay. It, so basically, it looks like it's 2 pi. Why? Well, you can have a frequency. Again, I'm not a mathematician or something, but I'm pretty sure like that whole you need to go by 2 pi to have your full revolution or go through your full wave oscillation and stuff. So I mean that that should make sense, right? I just and again, it's just I don't know. At the minimum, in order to get the energy, we need a circle or a cycle, and then perhaps at a some form of a maximum, we need another cycle. I don't know. But it is a very interesting thing. I don't know. Do things need to come full circle? Might that be a fundamental principle of reality? I can't say. But I'm thinking we could figure out a lot of this stuff. I'm pretty sure I've had some very interesting conversations, and let's just say there may or may not be movie. Listen, I'm only a dude. I talked to some very interesting people. And again, there's plenty of folks I haven't spoke to, but I believe that there's some very interesting folks out there that have a lot of different ideas. Heard a lot of different interesting things kind of going on that may be proposed to help maybe open up some opportunities for other folks uh, to help contribute and stuff. I know Stephen Wolfram, we did his blog piece, and then I cut out like the last like 10 minutes where I basically just ignored everybody and just basically the last part is he's giving his opinion and his advice on what people could do, typically in regards to contributing if you're not a traditional academic researcher or within a standardized institutional setting, so to speak. Um, Also, if people want to send things to him, that's the thing. It's like he's like, I'll get all these things, and even when I talk to him, I'm like, it's got to be some interesting things in there, but I'm like, it's like, yeah, almost. It almost doesn't happen. It's very often it's like you got somebody they're just using some general high school physics, or maybe they're sending something that if you had to spend a little bit of time searching what also might be out there, maybe it was already solved 100 years ago or something like that. Because even at one point, like, listen, well, yeah, maybe it could help you with something, but typically it's if you're trying to get it to do something, at least right now, more novel. It if you're asking about something that it read online and has a very clear answer to, that could be a very good learning tool because, while that might be something that was discovered by somebody else or formulated years ago, it might be new to you. And at least for me, I don't really know anything. So there's plenty of stuff I can learn. Uh, you also have to be careful going down rabbit holes because even that little thing with the 137 like what is it micrograms or something like that there. I lost my mind for I think like half a day or a day on it, and then eventually I just put in more significant digits, and I'm like, yeah, yeah, like if it was like 2 pi away from the 137, or it was like I could multiply by one Geeskian constant, I could at least attempt to. Yeah, I couldn't find anything to work. Nothing, nothing useful that I could find to try to justify any significance, and that's I just gotta chalk it up to. A little coincidence and just rounding right there. So that's also one of the other things because it's I don't know. Sometimes I'll see like different videos and stuff, and it's like I'm gonna say it's like, well, you have the what is it the golden angle? It's like 137.5, and then it's like, well, this is you can think of this as the fine structure constant. It's like, but the fine structure constant when you express it by its inverse or and not using its amplitude like Professor Feynman and that kind of generally talk about it. But if you're expressing it as that 1 over 137-ish thingy, it's not a 137.5. It's 137.0359999. And then we argue after the 10th digit, or perhaps there's an observational difference that happens around the 10th digit. Does it depend on the experiment? I don't know. Uh, but it's like, all right, well, you have the first three digits, significant digits, cool. But then you're trying to say that that five is equivalent to a zero. But I think you're also I don't know. I'm sorry. I'm hating on a person in it. Apologies. It's just also if it's angle and you're expressing maybe. Now again, I do some crazy stuff. even need to justify what the heck I'm saying. And again, I don't know. You have to be careful because also, to be fair, for a while there was a good deal of time where we literally were correct about the speed of light to zero significant digits. Because we were saying it was 3 times 10 to the 8. At least within our SI system, it appears to be 2.9979, or maybe it's 8 times 10 to the 8 meters per second. That's a little nitpicky because it agreed for at least about 3 significant digits, and a lot of people will still use it. And just rough calculation, yeah, seems to work pretty well. Ah, where? What was it? Divide by 137 to extract. I, I don't know if there was charge. Oh, hold on. Let's do make another thing. Planck. The difference between strong force and the electromagnetic force. It's yeah, it's about the fine structure constant. Oh, wait a second. Energy. Shit. Blah, blah, blah. Okay, yeah. Okay, 10 to the 7 joules. Okay. 159 nanograms. Uh, cool. Where were we? Uh, oh, cool. No, this is just Wolfram Alpha. This is just a website, man. Hold on. All it is you just go to wolframalpha.com. Literally just this. You can just use natural language to type in the Planck thing. So it's like, Planck time. What's that? Oh, this. Planck length. Here's the thing. In, in Professor Wolfram's piece, he talks about people will send him sometimes things just using an explanation in words. And it's like, yeah, kind of like once we got past like the 1600s and stuff, you kind of try to need to put it at least in some more stuff there. Now, again, I'm not saying you can't make a philosophical argument and stuff because what's Gödel's incompleteness theorem is phrased in such a way. So it's like, all right, if you believe the rules within a system are true, you cannot prove the statement within that system of rules without going in the outside. Oh, okay, so that sounds like you would need to be a hyper observer, or take a quote unquote God's eye view, so to speak. Uh, But all the other Planck things in there, like Planck power, according to the Wolfram Physics Project, a maximally entangled observer, whatever that might be, would output the Planck power. What is this? 10 to the 52 watts. What the heck is that? Okay. So it's expressed in power. Is watts, so we can click on this. So long story short is watts is energy per second. So we divide by 1 second. Yeah. Oh, sorry. We need to multiply it by seconds. I apologize because power has the third derivative. If I was dimensionally accurate, power is mass times area or length squared, and then divided by time to the third. We got -3. I went in the wrong direction. So that means that it is giving out 3.628 joules per second, aka 2 times 10 to the 5 relativistic mass energy equivalent of a solar mass. So basically, it's outputting the mass energy equivalent of about, what is that, 3,000. It's outputting the energy of about 100,000 suns per second. So, okay, this is the relativistic. It's putting out 10 to the 35 kilograms of mass per second. Okay, what does that mean? That means if we take Sagittarius, I'm spelling this wrong, Sagittarius A star mass. So if we take the mass of Sagittarius A star, aka what we believe or characterize as the supermassive black hole in the center of our galaxy, a maximally entangled observer would be putting out the mass energy equivalent of Sagittarius A star in 21 seconds. What? What? What does that even mean? Caveat, caveat. There's a poster sitting over there that I speculate it. I speculate it at least has an explanation for what that might mean. Um, because essentially, you took all the massive Sagittarius A star in 21 seconds. A maximally entangled observer would output that mass energy. That's freaking crazy. Might be a good source to run some, I don't know, hyperdimensional computer or something like that. I don't know. It's rampant speculation on my part. Uh, the little talking about, I wonder if there's a photon that falls out if we remove charge. I think a photon is, well, we consider it an oscillation in the electromagnetic field. So, I mean, to be fair, it's if it's within some frequency of something. I mean, we were talking earlier, like the Planck frequency, and again, there is some work out there that you don't really see many people talking about, but I don't know. And again, however you want to parameterize it, I personally don't think there's necessarily one correct way. I don't think you can do it. I think there's more than one way to do it. Maybe there is just one correct way. Maybe there can only be one. I think there are more effective models to model ways to model things, and there might be simpler ones. And again, I look at things for like maximum explanatory power. If you can explain more with less, that sounds like a win to me. At that point, it's like, I mean, you can complain about something being numerology, but it's again, I think at least according to history, like this this whole stream is supposed to be about Planck time. The Planck time, the first word in this is Planck. Pretty sure, and again, could be wrong, he derived H, Planck's constant, in its original form by looking at the data, pouring through this, and being like, what the heck would I need to put in to make it work? Happened to be about 6.6 times 10 to the minus 34 joule seconds. And then if you divide it by the rotation there, or 2 pi, now you get the unit h bar. But wait. You could say it uncharitably. 'Cause you could say he had the knowledge and the insight to look upon the data and realize what worked. You can also just say, dude, man, did a kludge, found something that worked, and now in modern science, it gets used all the time. I think it's a little bit more than a kludge, because when you actually look at some of the things, and have I gone through and done all the derivation stuff, something about like 91 nanometer wavelength or something like that. Because he was looking at it, it's like, okay, what do we need? We would have to chunk it this way. Bada boom, bada bing. Seems to operate reality. Realize I aggravated a lot of people with that statement, but that's okay. Uh, oh no! Don't worry about it, Bill. It's that's I ask questions all the time, and It depends on when it's asked. Whenever a person temporally gets back, because sometimes a question was right on when it was asked, but then I don't have a broad enough memory to remember everything I was talking about. Heck, I forget what I said, like literally like a few seconds ago. If you asked me to repeat all the words that came out of my mouth, that's what YouTube's for. Gives transcripts and stuff. So makes it easier to parse through. But yeah, no, that's all about what I got right now. Hopefully, I actually did some talking about Planck Time. I probably should have actually used the board. Could probably take that poster down. Seems not a paradigm drift until next month. Uh, but yeah, that's all I got for now. As far as we understand it, Planck time seems to be the minimal interval of time that seems to make sense according to our standard model that we have here. Does that mean that there might be stuff below it? Might there be further turtles down? Might it be how Rick says that time may potentially be a bottom turtle? Will Elandauer extend to the maximum of our universe, so to speak? Guess we're gonna have to stay tuned next time. So that's all I got for right now. Peace out, everybody. Take care of yourselves. It's a wacky and wild world out there, but it's open for a better tomorrow. Peace out, everybody.